going to discuss a paper by Nikolay Nifantiev. Title is Acid Catalyzed Transformation of the Pyranosides into Furanoside as a tool for preparation of furanoside synthetic blocks. So what they wanted to do here actually is, so before these papers, they came across so many literature where people are getting the byproduct as a furanoside. So, and also they saw so many reports where furanoside was a key glycoconjugate for the so many uh, microorganism like bacteria, fungi, protozoa, so many. So they wanted to mimic the same protocol to synthesize the furanoside. So whatever report till now there was, in that those cases, that traditional way, the starting material like let's say one monosaccharide with the large scale and having a lot number of steps, and also the kinetic control was there to get the selective furanoside. Still people were getting very less yield to coming across a number of steps, and as well as the number of manipulation of the protecting group, all the hydroxy groups. So in this group only, what they have reported previously, they have taken this allyl glycoside where the C2 and the C4 free hydroxy was there. Here, even not only two, so three hydroxy were free. C3 was protected with the BN group. So what they did, so they took the sulfur trioxide pyridine and the chlorosulfonic acid. They did the per sulfonation followed by the or desulfonation, leading to the pyranoside to the furanoside. So here this was the way it was going. So first this persulfonation was happening, followed by the protonation of the endocyclic oxygen, and then the C4O minus and the C2 sulfate O having there is a interaction with the C1 as well as the endocyclic oxygen. Then this C1 and O5 oxygen bond was breaking and forming the pyranoside, and followed by this hydrolysis by using sodium bicarbonate and this HCl pyridine complex in the DMF dioxane. They were able to get this uh, pyranoside, followed by the hydrogenation condition. They were able to remove this OBN group to get this free pyranoside. So they monitor through the NMR also. They were able to see the shifting of the NMR peaks compared to the pyranoside to the furanoside. So they were key shift of the anomeric carbons like C1, which was shifting like near 100 to above 105. And like that C2, C3, C4 were shifting little downfield. The same paper, they took one more example where they uh, first they took the same starting material. C3 was protected with the OBN, and C2, C4 and C6 was free. Then C4 and C6 was protected with the S2 protection, followed by the protection of the C2 with S-diol group, and then they removed the S2 protecting group, and then they did the same reaction. In that case, they were not observed this furanoside formation. So what they concluded there, in that paper, there should be C2 and C4 should be free. That should undergo for sulfonation. Then that only like force for the furanoside formation. There also this did this many example for the glycoconjugate synthesis, having the furanoside as a building block. So in this paper, what they have done, they have taken this benzoyl protected methyl glycoside. In this case only the C4 hydroxy was free. They took this triflic acid in the DCM. They saw there is a formation of the furanoside. So to so what they wanted to do here, they wanted to see in the like systematic way or the forward synthesis scheme, so that they can control the synthesis of this pyranoside. So that they started this experiment in the NMR tube by using this solvent system. They have taken this deuterated dichloromethane and the acetonitrile, toluene, and the DMF. In the case of deuterated dichloromethane, they were able to get 1:3, means furonoside. In case of acetonitrile, the pyranoside was more, and in case of toluene, the furonoside was more. But problem was, see, the toluene is less polar solvent, so it was not able to solubilize completely. And in case of more polar solvent, the acetonitrile case, they were not getting the selective furonoside. So what? So here they took this deuterated dichloromethane as a solvent in the SD condition to to proceed further. So here they have taken these many example of the galactoside. In case of methyl glycoside, allyl, and the isopropyl, like 135, they were seeing in same condition, the furonoside complete conversion was there. But in case of 7, this thioglycoside, so in that case, 40% was conversion was there, and compared to the 1, 3, and 5, when they came to the O-phenyl or this protecting TBMP, in that case, there was no product formation was there, the furonoside, even though the protecting group was same. So that means altering the protecting group at C1 also, there is a role of uh, protecting group at C1. In case of 13, when they changed this BZ group to O-phenyl, in that case, they were also able to see the like good conversion compared to the 1 to 5, like is comparable with 1, 3, and 5. But as well as in that case, little decomposition was there. Then they changed benzoate to the acetyl. In this case, there is a conversion of the furonoside, but this star was showing there is a acyl group migration C3 to C4 that was creating problem. So again, they fixed the protecting group just BZ, and they also tried with the BN when the BN was at C3 and the C6. So they got the similar conversion as they were getting in case of 1. But once they are putting the OBN group at C2, in that case, there was no conversion at all. That means here they change the protective group at C2. When they change this 21, 23, the configuration at C1 as well as C4. In this case, this alpha galactoside, and here is glucoside, beta glucoside. In both cases, they were able to see little conversion of the furonoside. Along with that, there was a decomposition of the starting material. So that, and in the case of 25, in the case of 25, when C2 was free and the C3 and C6 was protected with the OBZ, in that case also they were not able to see this furonoside product. So here what they have concluded is the acyl group should present at C2, as well as the configuration of C1 should be beta, and the best is the methyl allyl and the isopropyl, as well as the C4 should be free. So that was the case with the C3, compound number 3, allyl glycoside. So they carry forward with the compound number 3. They have taken this compound number 3. They did the same reaction at even higher scale. They were able to like scale up this reaction at 2 gram. They did the pyranoside to furonoside conversion, And then C4 was protected by this chloroacetyl group and followed by the allyl group conversion to hemiacetal, and then they made that hemiacetal to the TCA donor. And TCA donor, they took this acceptor 29, where they have taken this linker at anomeric. They did the glycosylation with the pyranoside, both furonoside donor and acceptor. They're able to get beta 1,1,5 link disaccharide with this linker. So before that, whatever report was there for this furonoside synthesis of disaccharide with the linker, that was very poor yield. So here they were able to they were able to show the yield of this reaction at 84%, followed by this deprotection of the ester group. They were able to get this free disaccharide, that is the antigen for the Aspergillus fumigation galactomannan. They undertook another pentasaccharide antigen, where they have started again with the C4 pyranoside, and they have taken this TCA of the protected glucoside, TCA glucoside, and this after glycosylation with the timsiflate, they got this disaccharide, and this R was the allyl group. In the previously, they did the modification of allyl with the using palladium chloride methanol in the lithium. In this case, they did not repeat the same reaction, even though they tried hard. So they changed the protocol. They use here iridium catalyst followed by the I2-THF water. And then they converted Li to the hemiacetal. Again, they made that hemiacetal to the TCA of disaccharide. Then this disaccharide was a donor of TCA, and this linker attached glycoside was the acceptor. They were able to get this trisaccharide. And then this trisaccharide, they removed this here R group with the hydrazine levulinic acid by using hydrazine in acetic acid in pyridine. So they got this trisaccharide acceptor where this C3 was free. And again, this 35, this disaccharide donor, again they took and they did the glycosylation. They got the pentasaccharide, protected pentasaccharide. And in this side, they took this monosaccharide donor to get trisaccharide here with the linker attached. Then again, first they remove this benzidine protection by using TFA, and then hydrazine in ethyl alcohol in reflux condition to remove the phthalimide as well as this levulinic group, followed by the acetylation of the amine and the free hydroxy, and then again deacetyl all the hydroxy group, followed by this CBG deprotection by using hydrogen palladium condition. So they were able to get this pentasaccharide in good yield. And this side, the same protecting group over there, they followed the same deprotection method to get this tetrasaccharide antigen. Here they also showed how this pyranose converting into the furanose. Here they determine the rate constant. As you can see, the time is increasing. The pyranoside is coming down and the furanocide is coming up. Means the concentration of the furanocide is increasing. Even when they took the pyranoside also, it is not coming down. It is same condition. The furanocide is not coming. Means the concentration of the pyranoside is not increasing over the time. The same group reported where they have shown even this intermediate um, like um, intermediate free galactoside can be converted in the furanocide by using the similar condition. And also they did the double PAF rearrangement, this pyranoside to furanoside rearrangement. Thank you.
Bharat, nice presentation.
Thank you. Thank you.
In first paper, they have shown C3, C2 should be the, go to that page first.
This is the
history or-
paper. Yes.
So C2 also should be the that functionalization, that SO3 minus, and then only it will go undergoes to the pyranoside to the furanoside.
Yes. So what they showed here. So when they are using this kind of free hydroxy of the sugar glycoside, so this C2 sulfate and the C4 sulfate forming this intermediate. When they
Yes.
are taking this example where this C2 as a acyl group, and also this C2 should be acyl, so that acyl group will form the similar intermediate, like here it is forming. In this step, if C2 will be acyl, this will form the same intermediate, and C4 should be free. And then since they are not doing the sulfonation, then C4 is the configuration of C4 only matter if it is like axial, that means the galactose, then only they are getting the pyranoside.
Okay, so there is no any problem with that SO3 minus. If there is C2 is acyl, then also reaction will go.
Yes, that only they showed in the next paper. Yes, that
Okay,
acyl group should be there at C2.
And in next paper, all the protecting groups are benzoyl, and only C4 is free. In that case, that reaction is going. So similar kind of mechanism again.
Similar kind of mechanism. The only consideration is this should be beta, and C2 should be acyl, and C4 should be axial, means galactose sugar.
And in the case of 19, they have shown if there is a PN, there is no reaction, right? 1H0 means
there is no reaction.
Nothing.
Yes, double star means there is no reaction at all. And with acyl, there was a migration of the acyl group, so they did not go with the acyl group, they went with the BZ group itself.
Migration?
Migration of acyl group C3 to C4. So that means that is controlling the yield, because C4 should be free. If there is acyl migration at the C4,
Yes.
so so that mechanism will not follow then. That intermediate
And
will
in
not
some
form.
glycosylation, they have used TCA, like derivative kind of TCA. You have seen
Yes,
that?
yes, and phenyl
Trifluoro.
yes.
So why they have used, why not the normal trichloroacid?
It's very much established donor mass. It's like people are using. It's little stable compared to the whatever trichloroacetonitrile we are using. It's like
In
little
one case,
selective and stable.
Okay, see 33 and 39. They have used both normal TCA. We are using trichloroacid and trifluoro also they have used.
So this N-phenyl one, this is little stable, but there is no change. There is no such difference in the reactivity. Both are very good donor.
Something in selectivity?
Not as such, because here they are getting the every time whatever they have reported is exclusive, whatever configuration they are getting, either alpha or either beta. But since whatever protective group they are using, that forming as a beta only, beta configuration.
Okay, yeah.
Good presentation, Bharat.
Yes, bye.
So my question, they used acid. So any Lewis acid also can use this reaction?
Oh, they did not discuss in this paper. They only just went with this solvent system. So what they have suggested is, when they are using this acetonitrile, means the more polar solvent, in that case, they are not getting the selectivity, means the conversion of the furanoside. And when they're using this less polar solvent, toluene, D8, in that case, the conversion was there, but there was a problem with the solubility. So they went with the in between the polarity of the solvent. Just they mentioned that much only. But since whatever glycosylation we are using in the motivation of this work was, since there were people are reported that there is a conversion of they're getting byproduct as a furanocide. So just they wanted to like there is a proper
Complete
scheme
this
where people
parentage.
can get the furanocide.
But furanol is
Obviously it can work
forming
for
in the
the
reaction.
sorry.
Furanol is forming in the reaction as a byproduct. For that,
Yes,
they try to conclude this work in a paper, how it is
yes,
forming.
yes. So they basically develop a proper scheme how one can get the furanocide.
Okay.
Yes.
They don't optimize like acid and other things.
Obviously, like it's needed the acid condition, because then only this protonation of the endocyclic oxygen will be there. Once this protonation of oxygen will happen, then only this C1 and O5 bond will break. Until unless this
No.
bond will not break.
Okay. But another OH is free now. This also will protonate.
Obviously, so like
Then
the
how it will do attack?
see the protonation of this bond. See, any bond can protonate. Any oxygen can take proton.
Huh.
So after protonation, there will be no reaction. So there is a driving force. Once this bond is breaking, this C4 is free, and this C4 is interacting with the C1, and also this C2 group also like stabilizing the whatever intermediate is forming. If you see the first is so here, so there is an interaction with this C1, C2, and the C4 group. That's why this protonation is helping for the furanocide conversion.
Yes, but in case of OH3, this OH3 also protonated by acid.
True. So
Then
if you
how it
see
will
that,
attack on positive
so
charge on OH?
let's say that OS is protonated with the H, so
Huh.
that can interact with the endocyclic oxygen, and then C2 will come, and that interaction will lead out to break this bond. No matter if that will take no problem,
Okay.
then that will deliver to the hydrogen to the C1 means O5, and that will become OH, and then that will attack to the anomeric.
Okay. This reaction they are getting 83% yield, not equilibrium with pyranose ring.
No. That's what they showed I showed in the last slide. Like even
Okay.
they took the furanocide, and here they took furanocide in the same condition that was not coming back to the pyranoside. So concentration of furanocide was up only,
That means pyranoside is more
and the
stable
rate
compared to furanose.
the rate of also conversion of furanocide to pyranoside is less compared to the pyranoside to furanocide.
Okay. Okay, Via. Thank you.
And this example they are only showing in case of galactose.
Only galactose. They took the glucose here on this example where 23 they are on this configuration of C4. So in that case, just they
Not too
got
much
5%
conversion.
yield, just 5%, and that this starting material was getting decomposed.
Nice presentation, Bharat. So by now what we understood, this is happening in galactose only mostly. So already we know that galactose is known for to stay in furanose form. Maybe that is thermodynamically stable more.
Exactly.
There is the role of thermodynamics and kinetics is also there too much. That's why it is staying there.
True.
Because in another case also, not in this C4 free, some of the time while doing glycosylation in anomeric position in free sugars, it is very common to observe this furanose product in galactose.
Yes,
but that is not happening in other sugars.
exactly. They cleverly they took the galactose firstly, and since there was a there are so many reports where people have reported that this just reported as a byproduct. But here
Yeah.
they just showed one, okay, we can get, if you want the furanocide, we can get furanocide by using this method. And also they showed this synthesis of this antigen by same method to establish and also to, okay, say like this is the way we can get furanocide and can be utilized further for the glycoconjugate synthesis.
Yes, because I think before this everyone knew that while doing anomeric glycosylation, furanose will get in case of galactose. But this problem they have addressed with keeping the another OH.
Another way. Yes.
Yes, reverse way. But I think
Yes, as you are
resulted the
telling,
same, the
the
driving
kinetics,
force is same
people
on.
earlier, they are using the kinetic control to get the furanocide of the galactose,
Yes.
manipulating the group, protecting group. So here they chosen only one kind of sugar with keeping the two thing, just C2-acyl and the C4 should be free OH. That's all.
But
Even
in
though if you are going with the thioglycoside also, they were not able to get this furanocide with the O-phenyl, with this TBMP, with the this only 3-glycoside, O-methyl, O-allyl, or isopropyl.
it means that O glycoside should be there.
O-glycoside should be there. Even O-glycoside with O-phenyl, in that case also, they were not get a little product also. There is no conversion at all.
So how they are defending that? It means the A glycan rule is also there. What A glycan moiety is there.
At the anomeric, exactly.
Yes.
So actually, this paper is completely based on observation. They did not show any mechanism.
Yes.
So
Okay.
just based on observation, so keeping different anomeric manipulation. So they claim that having these three uh, groups at anomeric, that will only help to get the furanocide. There is no proper mechanism at all.
They didn't propose also anything. Till now they
No,
are just showing the results.
yes, exactly. Whatever proposed mechanism they showed, that is in their first paper, this paper, how this going. And here they use this RHF, that is this Hartree-Fock, quantum people do calculation, quantum calculation. That much only they showed for the first paper. After that, just based on observation, they went with.
But in that case, they have deliberately taken this SO3. But in
Exa
normal glycosylation, keeping just normal protecting group is also able
yes,
to get the similar product.
yes. That's why they did not follow that paper. They went with this different condition using this acidic condition, acidic medium. Because we do glycosylation in the acidic medium, we are seeing the furanose formation in the acidic medium. So undertook acidic medium with the protecting group.
In any case, I feel this is good work only to at least help people. There's many examples they can select from.
Exactly, and also they showed this disaccharide, especially for this penta and all, they were showing people have prepared, but especially with the disaccharide, this one, people did not achieve more than 5% of this disaccharide yield with this linker to conjugate with something. So they are here shown 85% yield of this disaccharide with the linker.
In next scheme, what they are showing the trisaccharide synthesis.
No, ultimate goal of this antigen,
But here
this
no.
pneumonia OTAC antigen OA.
In this case, there is no conversion from furanose to pyranose.
So basically, this core only they used as here acceptor, and once they got this disaccharide, they took
There
this
is no.
disaccharide as a donor, where this furanocide was at the activist non-reducing sugar, reducing sugar. Sorry.
Okay.
And also here again they have taken this Pyranoside as a donor for the tetrasaccharide synthesis. So in between they have used.
But this is separate in this case. Like while doing glycosylation, it since other galactose they are not taking, so it won't go to
Exactly.
change. Okay, good. Thank you.
Thank you.
Nice presentation, Bharat. I
Yes,
have a
I-
general, I have a general question. Why this? Why they converted pyranose into furanose and then proceed further for glycosylation? Means what is the difference reactivity between when we choose pyranose or furanose?
It's not about reactivity. I told you like there are so many microorganisms are there where like the bacteria and the fungi and protozoa in their structure this pyranoside is there. So we have to mimic the synthesis of this pyranoside. So whatever sugar we're getting in the pyranoside form. So what they showed here. So how one can get this pyranoside and then we can do manipulation by using that pyranoside. So develop the kind of antigen for the similar pathogens. It's use case for the synthesis of this kind of antigen. It's not about the reactivity.
Okay, thank you.